I want you guys to go into this with the highest likelihood of understanding as much as possible as I can get you to have. That's my goal here, regardless of your current knowledge level for this topic. This paper is called The Distribution of CO2 on Europa Indicates an Internal Source of Carbon. It is by these two authors, and it is talking about the carbon dioxide that we already knew existed on Europa and where it most likely comes from. They narrow it down a lot in this paper. It is 1, 2, 3, barely 4 pages, and then there's some figures to go over too. We'll read the abstract in a minute, but we got some stuff to go over before we get into this, just to make sure that you guys enter this with as good of a foundation as I can provide you. We need to go over spectroscopy, the electromagnetic spectrum, some particular terms related to those, and there's a few chemistry-related terms that we should also go over. A lot of chemistry-related terms we will tackle as we go through them, or there's also like 5 chemistry-related terms that as we see them, I'll be like, I don't know what this means, but I don't think it's super important. There's a few of those, full disclosure. So let's go over very briefly first the electromagnetic spectrum, which is the foundation of the entire field of astronomy. The electromagnetic spectrum is just a fancy word for light. All of the light that we humans see is in what is called the visible part of the electromagnetic spectrum, which roughly goes from like 400 to, I think, 700 nanometers in wavelength. Wavelength is the distance between 2 peaks of a wave. So from here to here is wavelength, except this is not a great example because the wavelength here is varying. The rest of the electromagnetic spectrum is still all composed of light at different wavelengths. We just can't see it. Astronomy takes place in every single part of the electromagnetic spectrum. But depending on the field you're in, wavelengths are measured in different units. Here's the electromagnetic spectrum again. We have the longest waves over here. We have the shortest waves over here. And here they're measuring the wavelength in meters. Then around the microwave, they're measuring it in centimeters. And then around the infrared area, they're measuring it in that little, like a U, but one side is longer. That's called a mu, but as a prefix in front of a unit, it makes it micro. So those are micrometers. And then around the visible and ultraviolet, we use nanometers. And then when we get to the really high energy, really short wavelength waves like gamma rays and X-rays, we start using angstroms. For the purposes of this paper, the wavelengths that we're working with are around this area in the infrared. So they're measured in micrometers. Okay, let's move on to talking about spectroscopy. This is the visible part of the electromagnetic spectrum. I'm not here to go over the entire instrumentation behind this. You don't need to know that for this. But a huge part of the field of astronomy is observing sections of the electromagnetic spectrum and looking for what we call emission or absorption lines in those. When light passes through a material, that material causes these little absorption or emission lines to show up in the spectra. Oh boy, this is a lot to explain. I didn't plan out how to explain spectroscopy. I just said I got to explain spectroscopy to you guys. Spectroscopy begins by taking a section of the electromagnetic spectrum like this. This is the visible part of the spectrum. It doesn't have to be the visible part of the spectrum. The paper that we're going over, they looked at an area of the spectrum that has wavelengths from like roughly 3 to 5 micrometers, which is in the infrared. But for most examples, people use the visible light part of the spectrum, okay? You begin with this. This is what you get from stars. A star will give you a spectrum that's outputting roughly just as much light in all of these wavelengths, so you get something nice and clean like this. But then, when that light from this star passes through other material, depending on which element it encounters as it passes through, like gas or something, this light in question, that element leaves a unique, basically a fingerprint. Here are some examples. This top one is just all of these fingerprints combined, and then beneath it we have, if this light, this complete spectrum, passes through hydrogen and encounters that, these lines are missing from the final spectrum that we get. And then this is what it looks like for helium, and this is what it looks like for carbon, nitrogen, oxygen, etc. And we know what these patterns are for a lot of different elements and molecules. They're like fingerprints or like barcodes, basically. These are all what we call absorption spectra, which means that of the section of the electromagnetic spectrum that you're looking at, It is filled with light in every wavelength, except for some wavelengths of light have been absorbed by these elements that the light has encountered, so you get these dark bands. There is also an alternative one where you have no light, except light is emitted by the elements that you encounter, and then you get bands of color instead. That's called an emission spectra, but for the purposes of this article, I think we only really care about absorption spectra. When you're taught about spectra in your science classes, they show you these actual rainbows with these lines missing. And when you're actually taking spectra as data, you can get those, but more often what you're dealing with is something like this, where on the x-axis you have the wavelength, and on the y-axis you have something equivalent to like luminosity, flux, etc. Here they have it called transmittance. So at 1.0 here at the top, that would be 100% of the light is still reaching you, whereas here, 0% of the light is reaching you because it has been absorbed by some element or molecule that this light encountered. So this is an absorption spectrum because you have this baseline of 1.0 where you have all of this light, and then there are these dips where it has been absorbed. The way that these absorptions actually happen is that the atoms and molecules that this light is encountering have electrons. Big surprise. And every electron for every atom has a very, very specific wavelength that it will just eat if it encounters. It will absorb said wavelength, and then what happens then is that it gets quote unquote excited, and it raises in what we call an energy level. But that wavelength is very specific. So for example, you have hydrogen. Here's your hydrogen nucleus. And then you have an electron orbiting it. That electron, by default, occupies what is called the ground state. That is the lowest energy level. That means that this electron, here's the electron, has not absorbed any wavelength of light. However, if the electron encounters a specific wavelength of light that it can eat, that it likes, then it can jump up to the next energy level above that. Or depending on the wavelength it consumes, it can get to further and further energy levels. But in order for this electron to go from here to here, it needs a very specific wavelength. So in the case of hydrogen, we know all of those wavelengths very, very well. So if we look at this picture, which I know is a lot, you have the nucleus. This first blue circle is the lowest energy level. And then all of these grayish, greenish color lines are how that electron can jump to the next energy level and specifically what wavelength is required for that. So for it to go from the ground state to the second lowest energy level, it needs exactly 122 nanometers as the wavelength that it absorbs. Keyword absorbs. When that electron absorbs this, a specific one of these absorption lines in the spectrum forms. So say that 122 nanometer wavelength photon is absorbed by this electron and it makes this jump. Then consequentially, in the spectrum that you get, which we're using this one, this isn't actually it, where on the x-axis you would find 122 nanometers, there is going to be a dip because that light has been absorbed by that electron. Okay, when we look at graphs of spectra, and you have a dip like this, just a little thin one from a photon getting absorbed, we call that, you can call it like a trough, right? But I think we usually call it a peak because if you're looking at an emission spectrum, it's actually it goes up instead of down. So if you've got a little narrow one like this, it's called a peak. Also, when we're talking about light and spectroscopy, you will very often hear the term band. My understanding is actually that a band is basically just like a segment of something. Like we can use it to talk about a specific part of the electromagnetic spectrum, but the way that this paper uses it and that it is often used in spectroscopy is that when you have a larger, wider dip of absorption like this, that is called a band rather than a peak. But also, this paper uses it another way too. The paper also refers to bands in how we refer to different parts of the electromagnetic spectrum as being in certain bands. I will explain that when we get to it in the paper. But in spectroscopy, a band is a widened area like this that is caused by a lot of absorption or a lot of emission, I think. And then your bands, which look like this, sometimes are broader. If it's broader, it means it's like that, or narrower, which means it's like that. What determines that is... I'm specifically not going over the broadening that can happen due to like the Doppler effect. If you know about that, don't worry about it. We're not talking about it right now. I think it just depends on what materials it passes through, or at least I think that's one of the ways that bands can be broadened. A band is usually a sum of enough peaks that we can't resolve them separately. Both bands and peaks are spectral features that tell you information about what elements and molecules that light has encountered. Okay, that's the bottom line. They both serve pretty much the same purpose. They're both spectral features. We do also need to go over reflectance spectra. So this article says a reflectance spectrum shows the colors that reflect off a surface. Earth scientists use reflectance spectroscopy to study rocks, soil, ocean water, ice caps, mineral deposits, forests, farmlands, dust storms, blah, 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 and even wildlife. Planetary scientists use reflectance spectra to figure out what the surfaces of planets, moons, asteroids, and comets are made of. The pattern of colors that a material reflects depends on not only what colors it is absorbing and transmitting, but also many other factors like roughness, shape, and orientation. Reflectance spectra, this is important, are typically a lot more complicated than emission and absorption spectra and can be quite difficult to interpret. Yeah, they sure are. Reflectance spectra are what you get when you look at light that has been reflected off of a surface. And the surface that has reflected that light back at you oftentimes will have absorbed some of it as well. So looking at reflectance spectra can tell you about that surface that your light has been reflected off of. Europa is a very reflective moon, so we deal with a lot of reflectance spectra with it. Also, note that I said absorb in regards to what the reflecting material might do. As such, reflectance spectra are absorption spectra. Okay, and then the other thing that we need to go over before we get into this paper, this is just a quick thing, but you'll see these three terms in this paper a lot, so we need to clarify the difference between them. Organics, carbonates, and hydrocarbons. Organics are molecules that have carbon-hydrogen bonds in them. Hydrocarbons are composed entirely of carbon and hydrogen. If there's a CO3 in it somewhere, it's a carbonate. Okay, and then let's go over a little bit that I think we went over with the previous paper review that will be useful here. Europa is a moon of Jupiter. It is the smallest of the 4 Galilean moons of Jupiter. It has a surface of mostly water ice, and it has a subsurface ocean underneath that of salt water. Its exact composition, we're still kind of figuring out. Europa also occasionally has plumes on its surface that erupt out into space. It was Hubble that found those actually, but it doesn't have them as frequently as like Enceladus does. Enceladus is another moon of Saturn, another icy moon with a subsurface ocean. Another thing that we went over with the last paper that we went over is that Jupiter's magnetic field subjects Europa's surface to a lot of really intense radiation, and when that radiation interacts with species, that being molecules and atoms on Europa's surface, it has the potential to change or destroy their bonds, which can thus change the composition of the surface. Magnetic fields can strengthen, change, or break chemical bonds. The process of breaking apart molecules through exposure to ionizing radiation is called radiolysis. I think we can probably actually start talking about the paper now. Oh, wait, actually, another thing. So you have these very specific wavelengths that will excite these electrons to these extents. If an electron gets energized enough, it skips all of these and just leaves. And then that atom loses an electron and is ionized. Okay, I think we can actually start talking about the paper now. The distribution of CO2 on Europa indicates an internal source of carbon. Jupiter's moon Europa has a subsurface ocean, the chemistry of which is largely unknown. Carbon dioxide, CO2, has previously been detected on the surface of Europa, but it was not possible to determine whether it originated from subsurface ocean chemistry, was delivered by impacts, or was produced on the surface by radiation processing of impact-delivered material. What this last part means is that, say that an external body, like an asteroid, struck the surface of Europa and left some extra material there, and then Jupiter's magnetosphere irradiated that to change its species into other things. That's what this means. We mapped the distribution of CO2 on Europa using observations obtained with the James Webb Space Telescope, JWST. We found a concentration of CO2 within Terra Regio, a recently resurfaced terrain. This indicates that the CO2 is derived from an internal carbon source. We propose that the CO2 formed in the internal ocean, although we cannot rule out formation on the surface through radiolytic conversion of ocean-derived organics or carbonates. Let's clarify a little bit of what this means. Ocean-derived organics or carbonates. Organics or carbonates that are from Europa's subsurface ocean and have made it to the surface. Although they propose specifically that it formed in the internal ocean as CO2 and then made it up to Europa's surface. They mentioned that Terra Regio is a recently resurfaced terrain. Europa's surface overall is very, very young. There's a lot of resurfacing happening on Europa where material that is deeper inside of Europa makes its way to the top and then becomes Europa's surface and kind of pushes the other stuff aside. It's kind of like this sort of solid state convection that's happening across Europa. And it results in these areas where there is much more of this resurfacing activity called chaos terrain. If you look at Europa, you can see places where its surface is more disrupted than in other places. So these more round, scratchy areas have a lot more activity going on there than the bluer, icier looking spots. If you want to learn more about Europa's surface and basically get this really coherent map about it, this is on the USGS's website. Continuing, so Terra Regio right over here is specifically where they got JWST to take data for them, take spectra for them, and what they looked at in more detail. They also looked at an area a bit north of it, I think kind of like over here-ish, but we'll get to that. That's not as important as where they did most of their science, which is specifically looking at Terra Regio? I'm gonna be fucking that up the entire stream. Beneath the crust of water ice, Jupiter's moon Europa has an internal ocean of salty liquid water above a rocky seafloor. You're gonna see a lot of these numbers in parentheses. That's just them citing their sources. Pay them no mind. A potentially habitable environment. Assessing the ocean's habitability depends on its chemistry, including the abundances of biologically essential elements, bulk oxidation state, and available chemical energy sources. The ocean's carbon content is poorly constrained. Previous work has identified carbon dioxide on Europa's geologically young surface through its infrared V3 asymmetric stretch fundamental band. However, there was either insufficient spatial resolution to map its distribution, or too many limitations caused by noise and artifacts to determine the source of CO2. Okay. Infrared V3 asymmetric stretch fundamental band. What the fuck does that mean? This use of the term band is not to refer to a prolonged dip in a spectrum. This use of the term band is to refer to just a particular part of the electromagnetic spectrum. V3 tells you exactly which part of the spectrum. Infrared tells you more broadly that we're looking within the infrared part of the spectrum. I told you earlier, this paper mostly looks around like 3 to 5 micrometers. For the wavelengths that it covers, that's the infrared V3 band. Asymmetric stretch. So we're in the infrared, right? And in carbon dioxide specifically, certain infrared wavelengths can cause what is called an asymmetric stretch in the covalent bonds that hold CO2 together. That looks like this in the middle. I don't understand this super well. It's caused by certain infrared wavelengths, and it shows up in our spectra. That's what I can tell you. When it's a symmetric stretch, like this, by the way, I don't think it shows up in our spectra, but when it's asymmetric, like this, it does. So in their spectra, they're looking for the signature that this stretch in CO2 results in. And then this is just saying they're the first to look for this, here's why. Attempts to map the CO2 on Europa indicated a possible association with dark material that is potentially endogenic. Endogenic means derived from internal processes. But the results were ambiguous and difficult to interpret. It has therefore been impossible to distinguish between several possible origins of the CO2. Geologically associated CO2 sourced from the ocean, geologically associated CO2 produced radiolytically by surface irradiation with charged particles of native organics or carbonates, or exogenic, meaning outside Europa, sources, such as delivery by impacts of CO2-rich bodies, or radiolytic conversion from meteorite-derived carbonaceous material. So what we're talking about here, about the several possible origins, there's basically 2 different ways that are divided further again into 4 total different ways that this CO2 could have come to be. It could be that CO2 is on Europa's surface as CO2. Just boom, there is CO2 there. It could be that that CO2 that is there on Europa's surface got there originally from Europa's subsurface ocean and made its way to the surface. Or it could be that that CO2 that is on Europa's surface in the form of CO2 already and always has been was deposited onto Europa's surface by impacts from meteorites. Or it could be that there is other material on Europa's surface that is converted into CO2 or makes CO2 by radiolysis. Remember when I defined what radiolysis is? Yeah, it could be that. And then if that's the way that it's made, then the next question is the material that is radiolytically being converted into or used to make CO2, where does that material come from? Is that material native to Europa? Like, is it coming from the subsurface ocean and then making its way to the surface? Or is that material being delivered by impacts from meteorites? CO2 distribution on Europa. We analyzed observations of CO2 on Europa obtained with the JWST Near-Infrared Spectrograph, called NIRSPEC, Integral Field Unit, IFU, on November 23, 2022. The spectra have a resolving power R of about 2,700, sufficient to resolve a double-peaked structure within Europa's CO2 V3 band. Remember, I told you what the V3 band is? Which we find has minima at 4.249 plus or minus 0.001 micrometers, and 4.268 plus or minus 0.002 micrometers. So the minima in question, these are what we would otherwise call peaks. I think they also call them peaks later. And let's go back here. The spectra have resolving power R of approximately 2,700. Spectral resolving power. R is another way of expressing spectral resolving power. Recall that spectral resolving power tells how close together spectral features can be and still be detected. The last time we went over a paper, I think I told you guys about this. That is what it is. The spectral resolving power of a spectrometer tells you how close together spectral lines, those being the peaks, can be and still be distinguished as two separate peaks as opposed to just looking like one. So it's like resolution. Continuing, we measured the integrated band area, equivalent width, across the entire absorption feature in each spatial picture. Each spatial pixel, then mapped the resulting band strengths across the surface. So measuring the integrated band area, that just means like from your baseline here down to here, measuring the area under this curve. The larger that is, the more of that species you are detecting. The strongest overall CO2 absorptions were located in Tara Regio, a roughly 1,800 kilometer diameter area of geologically disrupted resurfaced material known as, I told you guys this, chaos terrain, that is among the youngest on Europa's surface. The formation of chaos terrain is not well understood. However, proposed explanations all involve large-scale disruption of the surface ice through interactions with endogenic material from below. Like that possibly kind of like solid-state convection that I mentioned. Such as upwelling buoyant material that is less dense than the material around it, going up to Europa's surface and reaching it. Subsurface brines. Now, subsurface brines, I think brine just means like salt water, rising pockets of salt water, or lens-shaped formations of liquid meltwater. So the lens-shaped formations of liquid meltwater, you might recall from the last paper that we went over that I talked about shallow meltwater lenses and basically described them as puddles. That's wrong. They're not puddles. They are subsurface. They are lens-shaped subsurface pockets of water that is there because some ice has melted, thus meltwater. So another way that I worded this in my notes is that there are several different possible causes of chaos terrain. Upwelling of warmer ice, rising pockets of brine, or subsurface shallow lens-shaped deposits of meltwater. Basically, Europa's surface has a lot of material being transported in both directions towards the surface and away from it, on timescales of thousands to tens of thousands of years. So those are really short timescales. And the transport of that material, especially upwards, is what causes these chaos terrain areas. But like the specific method of transport for that material is what we're not super sure about. Those three options are some of how it could happen. There's another paper about this that I will link in the Discord, Active Formation of Chaos Terrain over Shallow Subsurface Water on Europa. I think this paper is specifically where the idea of meltwater lenses comes from, And then there's also, this graphic is a little bit more complicated than what we actually need to go into in depth, but it does show you that this is one of the models that shows you transportation of material through Europa's shell. This is actually specifically showing you how material goes down towards the ocean, but there is this. This is part of this article. I can link it. So those are 3 of the possible ways that material could be transported from Europa's subsurface ocean to its surface and result in this chaos terrain. Terra Regio has previously been inferred to contain salty endogenic material. Sodium chloride has been detected in the region and interpreted as ocean-derived, and it also contributes to the discoloration of Terra Regio relative to the surrounding regions. I have one small note here. Fun fact, salt, NaCl, sodium chloride, turns brown when it's irradiated. Look at Europa. So that's fun. I think that's pretty cool. CO2 is also enhanced within portions of Powys Regio, another large-scale chaos terrain, although it is less well resolved by the JWST observations. This region also exhibits generally weaker signatures of endogenic NaCl than does Terra Regio. Potential exogenic sources. So as they said in their abstract, they pretty much rule out the idea that the CO2 on Europa is from exogenic or external sources. But you gotta be a good scientist and explain why, so that's what this next section is about. The association between the CO2 band and Europa's geologically young, resurfaced chaos terrain indicates a relationship between the surface CO2 and Europa's internal chemistry. Nevertheless, we considered the possibility of exogenic origin. CO2 has also been detected on 2 other moons of Jupiter, Ganymede and Callisto, and throughout Saturn's satellite system. Unlike that found on Europa, the CO2 on Ganymede is preferentially associated with dark, non-ice material in the oldest and most heavily cratered terrain. Recall what we have heard from the abstract and what we've read so far, CO2 on Europa is most abundant at the youngest, most recently resurfaced terrain on Europa. Okay, remember that. CO2 on Callisto is associated with impact craters and has a hemispherical distribution consistent with exogenic processes thought to be associated with Jupiter's co-rotating magnetic field. Exogenic meaning from not Callisto, right? From outside. Previously suggested explanations for the CO2 on Saturn's icy satellites include the delivery of CO2-bearing impactors and radiolytic production from externally derived carbonaceous materials implanted into the surface ice. Remember what radiolytic means? Radiolysis is when molecules are separated or split by ionizing radiation into other atoms or molecules. That's important, we talk about it a lot. None of these scenarios would produce the observed relationship between Europa's CO2 and its geologically disrupted large-scale chaos terrain. Basically, this is saying the pattern of where we see the most CO2 on Europa doesn't make sense with any of these methods that creates the CO2 or delivers the CO2 onto Ganymede, Callisto, or some of Saturn's moons. If the CO2 were externally delivered, we would not expect it to be supplied specifically to terrain formed through endogenic processes. If instead it were produced radiolytically from carbon-bearing meteoritic materials, we would expect a distribution reflecting the external implantation, radiation intensity, or both. The leading hemisphere of Europa, where Terra Regio and Powys Regio are located, is thought to receive more meteorite impacts than the trailing hemisphere, but there is no reason to expect that input to follow the distribution of chaos terrain. The low latitudes, this part, my homies who were here for the last paper will know this part. The low latitudes of the leading hemisphere receive higher fluxes of greater than or equal to 20 mega electron volts energetic electrons in a longitudinally and latitudinally symmetric lens-like pattern centered on the leading point. This pattern does not resemble the highly asymmetric, geologically correlated distribution that we observe. Remember with the last paper, we looked at which parts of Europa are subject to the most intense radiation, and it follows this lens-like shape. What this paper is saying in these last 2 sentences is that this lens-like shape is different from where the chaos terrain on Europa is located. As such, they don't suspect that the CO2 is caused by radiolytic processing of exogenic material delivered by meteorite impacts. So if it was done by radiation affected by Jupiter's magnetic field, we would expect to see it in a very specific pattern focused on the areas the radiation hits the most, but instead it's location based on geography. Yeah, exactly, yes. To be stable under Europa's surface temperatures and pressures, CO2 must be trapped within a host material. This is another really important part of this paper, okay? I think the really important parts of this paper that we've gone over so far are endogenic versus exogenic. What do they mean? The possible ways of chaos terrain forming on Europa, the 4 possible ways that CO2 could be formed on or be delivered to Europa. And now we got another one. To be stable under Europa's surface temperatures and pressures, CO2 must be trapped within a host material. We therefore considered the possibility that CO2 is produced uniformly across the surface from exogenically implanted material, and then somehow trapped more efficiently within chaos terrain. However, there is no evidence for a connection between chaos terrain and minerals known to trap CO2, including amorphous ice and phyllosilicates. I cannot tell you what amorphous ice and phyllosilicates are, but they're dismissing that anyway. The NaCl that is known to be enriched in Tara Regio does not contain the necessary trapping sites in its mineral structure. Salts cannot trap CO2. At least not the salt here. We consider whether optical effects associated with grain size differences and the dark salty material in Tara Regio could enhance the observed CO2 band depths in this region. Larger ice grain sizes cause photons to encounter more dark particles of non-ice material, which would enhance band strengths if that material were the host for CO2. However, Tara Regio has been suggested to contain smaller ice grains than those found in its surroundings, which precludes this effect, and an equator-to-pole increase in grain size has been generally inferred across Europa's surface. This is talking about differences in the structure of the water ice and how that could affect or distort the spectra that they get, and basically dismissing that as not a factor that is influencing their research. After considering each of these scenarios, this is big, we reject the possibility of an exogenic origin of the CO2. Like I said here, they don't think it's exogenic. Like they said here, they don't think it's exogenic. Instead, we infer an endogenic origin linked to the geologically young chaos terrain. So recall here where there were 4 different possibilities in similar pairs, 2 of them endogenic, 2 of them exogenic. We've ruled out 2 of them. It's not exogenic. Now, potential endogenic sources. This is more important because this is where they actually think the CO2 is coming from. In principle, CO2 might not be the original form of carbon delivered to the surface, but could instead be produced within Tara Regio from the irradiation of emplaced organics or carbonate minerals by the greater than or equal to 20 mega electron volt energetic electrons that impact the leading hemisphere. Remember these from the last paper? And then remember the production of CO2 from irradiation of these things, the radiolysis, remember? To investigate these possibilities, we searched the JWST spectra for spectral features around the CH stretch bands of possible organics, from about 3.3 to 3.4 micrometers, or the 3.4 and 3.9 approximately bands of carbonates. Recall, organics have CH bonds, and carbonates have CO3. Basically, they're looking for these spectral signatures of the species that could possibly result in CO2 through radiolysis. That's what this sentence is saying. And then these numbers with the micrometer wavelengths are telling you exactly where they would expect to find those spectral features. These signatures of organics have been detected on other icy satellites, including Enceladus, Iapetus, and Hyperion. Wait, oh my god, I forgot to even look at, I knew I was going to do this. I forgot to even look at these pictures. Okay, pause. It wants us to look at figure 3a. We're looking at this first. Figure 1, which is relevant to their spectra. Continuum normalized spectra, smoothed with a 5-point moving average, are shown by the solid black curves. The solid black line is the spectra that they took. The dashed black lines indicate the continuum level. So that's the level at which you have all of the light. None of it has been absorbed by anything. The 2 band minima, so those are your peaks that indicate CO2 being there, are marked by vertical blue and red dashes at 4.25 micrometers here and 4.269 micrometers here. So A is spectrum extracted from a spatial pixel centered at 46 degrees north, 86 degrees west, in which the 4.27 micrometer peak dominates within the V3 band. Then when they look at section B, or sorry, figure B, figure 1B here, that's looking at a different point on Europa, 15 degrees north, 112 degrees west. And here, these 2 bands have similar depths. And then C is looking at a different point on Europa, 8 degrees south, 84 degrees west, where the blue one, the 4.2 micrometer peak, is dominating. They discuss this more later in the paper. Figure 2. Maps of the CO2 band area and the ratio between its two peaks. Okay, so you see this thing, this like chicken nugget creature on the right? That's Tara Regio. This. In both panels, the disk of Europa is indicated by a black circle. Whoa, crazy. Gray dashed lines indicate coordinates and meridians. The boundaries of a large-scale chaos region, Tara Regio and Powys Regio, are outlined in black within the disk. A is a map of the band area indicated by the color bar of the entire V3 CO2 band. So we're just going to use the water one as an example. If you take basically this area is going to be more if you've detected more CO2, although this is water's spectrum. Pretend we're looking at CO2's spectrum. This area is going to be more if you're looking at more of the species that you're looking for. So the orange places here, yellow, have more of that area, and then the deep blue, indigo sort of places have less of that area. So yellow means more CO2, blue means less CO2. And in Tara Regio, there is the most CO2 that they found. B, map of the ratio between the 4.27 and 4.25 micrometer and 4.27 micrometer peaks within the CO2 band. The spatial pixels outlined in white mark the locations of the spectra shown in figure 1. This is telling you that the ratio of these two peaks to each other differ with where on Europa's surface you're looking, and this is the color code that tells you that. Okay, we've gone over those figures. So we left off with these signatures of organics have been detected on other icy satellites, including Enceladus, Iapetus, and Hyperion, and carbonates have been observed in the bright spots of the dwarf planet Ceres. We do not detect any such bands in the Europa observations. However, the 3.2 to 3.6 micrometer wavelength region in the Europa spectrum is complicated by strong bands of water ice, a water ice reflectance peak at 3.1 micrometers, and a previously identified band of hydrogen peroxide, H2O2, at 3.5 micrometers. If carbonate salts are heavily hydrated, the characteristic bands can be suppressed and hidden by water signatures. An endogenic reservoir of organic or carbonate-bearing precursor material would produce stronger organic or carbonate bands in Tara Regio than in non-chaos terrains. We therefore divided the average spectra of Tara Regio by the average of another region to its north to enhance any organic or carbonate features. Okay, that's important. That's why they took a spectra of a region to the north as well. The ratio is dominated by broad differences in the background continuum and near the water 3.1 micrometer reflectance peak, as well as by the excess H2O2 already known to be present within Tara Regio. There are no features attributable to organic material. We therefore exclude the presence of an Enceladus-like organics band at 3.4 micrometers, with an upper limit of less than or equal to approximately 20% of the band strength observed in Enceladus Tiger Stripes region. Let's pause here and look at the figure. A, this one. Spectra of Tara Regio, green, and a location north of Tara Regio, blue. C shows you specifically where these spectra are taken. The black outline is, again, Tara Regio. Labels indicate the V3 band of CO2, right here. The 3.5 micrometer band of hydrogen peroxide, H2O2, right here. And the 3.1 micrometer Fresnel reflectance peak of water ice, right here. Is it Fresnel? I think it might be pronounced Fresnel. Also shown for comparison, this is important, are a spectrum of the Akator crater on Ceres, that is the dotted black line, this long one, which has absorption due to carbonate minerals, a spectral ratio of the Tiger Stripes region on Enceladus relative to its nearby regions, that is the dashed black line, this one, which exhibits absorptions interpreted as organics, and a continuum-removed spectrum of the trailing hemisphere of Iapetus, which is this dashed dotted line, which shows bands at approximately 3.3 and 3.45 micrometers due to aromatic and aliphatic organics, respectively. All spectra have been normalized at 3.6 micrometers, and the Ceres, Enceladus, and Iapetus spectra are offset for display by 0.55, 0.5, and 0.78 units, respectively. So what you're looking at in figure A here is that you have two spectra from Europa, one of Tara Regio, one of this blue region north of Tara Regio. And then you have these spectra from Enceladus, that's this one, Ceres, this one, and Iapetus, this one, that have distinct spectral features of carbonate minerals on Ceres, organics on Enceladus, and also organics on Iapetus. But the spectral features that are shown in these little spectra from Enceladus, Ceres, and Iapetus are not visible in the spectra that you see on Europa. See, like there's peaks here that are very clearly not in the Europa spectrum, and then there's a big band here that is very clearly not in Europa spectrum. And then B zooms in a little bit. B is the ratio solid black line between the spectra of Tara Regio and the region to its north from figure A, or figure 3A. The same spectra of Enceladus, Iapetus, and Ceres as shown in part A are included for comparison, with additional bands labeled. We attribute the 3.5 micrometer band in the ratio spectrum to excess water, so that is this excess water. That's what causes this little dip, which has previously been seen to be more abundant in Tara Regio. No other absorption bands are evident in the ratio spectrum, except for a less than 1% deviation from continuum near 4.0 micrometers. That's just, you pretty much can't even see it. There's a little something right here. Disregard it. It's so little that we can't say it's reliably actually even there. And then C, I don't think we actually need to go over in detail what C is. I think it's just, like I said, blue is the region above, the region north of Tara Regio, and green is Tara Regio itself. Looking at figures is so much more understandable with someone reading them. Really? I'm glad. Now we go back to the text, and we'll probably switch between the text and the figures a little bit here. There are no features attributable to organic material. We therefore exclude the presence of an Enceladus-like organics band at 3.44 micrometers, with an upper limit of less than or equal to approximately 20% of the band strength observed in Enceladus Tiger Stripes region. We also exclude the 3.55 micrometer band to a similar level. On Enceladus, this feature has been interpreted as resulting from organic material, possibly methanol, or alternatively interpreted as H2O2. On Iapetus, the aromatic and aliphatic bands are broad, but the 3.35 micrometer reflectance peak between them would appear in the ratio spectrum if this band were present. Okay, now let's go over specifically this Iapetus part. Iapetus, which is this one, dots and dashes. Oh, I didn't define for you what aromatic and aliphatic mean. Remember what hydrocarbons are? Hydrocarbons are materials composed entirely of carbon and hydrogen. Those are divided into two classes, aliphatic and aromatic. Honestly, I can't tell you more than that, but I got through this paper without knowing that, and you can too. Oh yeah, so also, this is a lot of numbers and a lot of units, but basically what all of this, all the way up to here, continuing all the way to over here, is saying that, like I said, the spectral features that you see in the spectra from Iapetus, Ceres, and Enceladus are not seen in any of the spectra that they got from Europa. Then when you get to like the numbers and the units, they're telling you like specifically which spectral feature. On Iapetus, the aromatic and aliphatic bands on Iapetus are broad. That's what this arrow, these two arrows, lines really are pointing to, is that there's a band here and a band here that are caused by hydrocarbons on Iapetus. And those are, I think what they're implying is that they're just too broad for them to feel confident discerning. However, there is a peak between them right here at 3.35 micrometers. And that peak, if these organics, these hydrocarbons were present on Europa, that peak would show up in the spectrum here, but it doesn't. Same thing goes with pretty much all of these other spectral features shown from Enceladus, Ceres, and Iapetus. They're not shown up in Europa spectra. However, we would not be able to discern similarly broad organic signatures against the stronger water and H2O2 absorptions if such a reflectance peak were absent, as would occur if the organics were dominated by either aromatic or aliphatic compounds. So far, in the potential endogenic sources, it's only been discussing so far how could CO2 be formed on Europa's surface through radiolysis of existing materials. That's why they're looking for these other materials that have been found on Enceladus, Ceres, and Iapetus. And recall in the abstract, they said that they cannot rule out formation on the surface through radiolytic conversion of ocean-derived organics or carbonates. So they try their best to rule out some of this based on these spectral features that they are clearly not seeing. However, the caveats that they have given so far is that if carbonate salts are heavily hydrated, The characteristic bands can be suppressed and hidden by water signatures. So that means that if there are heavily hydrated carbonate salts present, the spectral features that would tell them that these species are there wouldn't be visible in this spectrum. And we would not be able to discern similarly broad organic signatures against the stronger H2O and H2O2 absorptions if such a reflectance peak were absent. Okay, yeah, this is another caveat. If this reflectance peak were absent in Europa's data, which it is, then hypothetically, if these organics bands were still there, they wouldn't be able to distinguish them, I think is what they're saying. Okay, the ratio spectrum shows a less than or equal to approximately 1% deviation from the continuum near 4.0 micrometers. Recall, I tried to point that out to you, but you really can't see it, which is coincident with the strongest carbonate absorption band for Ceres Occator crater. This is consistent with a minor contribution of carbonate materials in Tara Regio. However, at 1%, we consider this potential feature to be too shallow and indistinct in shape to constitute a detection of carbonate, particularly because it falls close to the edge of a gap in the near-spec wavelength coverage. What this is saying is that this, almost, but definitely probably not a detection, is right on the edge of what the instrument can actually see anyway, so that data is a little bit less reliable too. So this 1% deviation, less than that, near 4.0 micrometers, don't count it as a detection of anything. We therefore put an upper limit of less than or equal to approximately 1% on any approximately 3.9 to 4.0 micrometer carbonate bands, which is equal to the observed depth of this feature. This is equivalent to a band depth of less than or equal to 2.5% of the band observed at Occator crater on Ceres. No organics or carbonates have been identified in higher spatial resolution observations of the same chaos terrain from ground-based observatories, which did not cover the CO2 band. Laboratory experiments, so they're saying that organics, they can't completely rule them out, but they don't think that the organics that could be used to create CO2 through radiolysis are present in these areas of Europa's surface. Laboratory experiments have investigated the electron irradiation of hydrocarbon and water ice mixtures at Europa-relevant temperatures, finding production of refractory long-chain aliphatic organic material and CO2. I just straight up don't know what this means. I think laboratory experiments have looked at scenarios similar to Europa's surface and looked at hydrocarbon and water ice mixtures and possible radiolysis that they could undergo and found that they did manage to produce these, I think. No equivalent laboratory experiments have been reported for irradiation of carbonates. The JWST data provide no evidence for such additional carbon-bearing material on Europa or preferentially within Tara Regio. We therefore prefer the interpretation that the CO2 we observed on Europa was delivered from an endogenous source already in the form of CO2. Okay, we got through all of this. What does it say? It says that recall, here we went over the 4 possible ways that CO2 could end up on Europa's surface, and then in potential exogenic sources, we ruled out 2 of them and said, okay, it's got to be endogenic. Now we have ruled out 1 more of them, mostly, in that it has to be endogenic, but they don't think that it is being made via irradiation and radiolysis of material that is already on the surface and is not CO2. They think that the CO2 on Europa's surface reached Europa's surface as CO2. Basically, they think that CO2 is coming from Europa's subsurface ocean and ending up on Europa's surface. Double-peaked CO2 band profiles. The JWST data resolved 2 discrete peaks within the V3 band of Europa's CO2. As seen in figure 1, you remember we got the blue line and the red line at 4.25 and 4.27 micrometers. 2 discrete peaks within the V3 band of Europa's CO2, which constrains its physical state on the surface. The 4.25 micrometer peak implies that the associated CO2 exists in a trapped form, causing the fundamental vibration to shift to higher frequencies than the normal position of approximately 4.27 micrometers expected for pure CO2 ice. So I think the vibration it's talking about is caused by that stretch in the CH bonds that we were talking about. And then if you just have CO2 ice, just frozen CO2, nothing else in it, you expect to get a spectral feature at 4.27 micrometers, which they found, and they also found a spectral feature that they attribute to CO2 at 4.25 micrometers, which implies that the CO2 in question exists trapped in some other material. Remember the key point earlier that I said, one of the big points this paper is making that you should understand? In order for CO2 to be stable on Europa's surface, it needs to be trapped in some other material. So them finding this peak at 4.25 micrometers aligns with that. So refresher before we continue, they found two peaks in their spectra that they associate with CO2. One at 4.25 micrometers, the blue one, and one at 4.27 micrometers, the red one. 4.27 micrometers is where you would expect a peak from pure CO2 ice. 4.25 micrometers is where you get a peak, probably because that CO2 is encased in some other material. It's not pure CO2 ice. Continuing. This phenomenon has previously been invoked to explain the stability and band positions of the CO2 bands absorbed on Ganymede and Callisto, although there is no consensus on the trapping mechanisms and host materials. There is CO2 on Ganymede and Callisto. We have found them at these locations in the spectra of Ganymede and Callisto. We are not sure what that CO2 is trapped in and how it is trapped in that material for Ganymede and Callisto. Ganymede and Callisto are two other moons of Jupiter that are, at least in terms of things orbiting Jupiter, the closest thing to siblings that Europa has. Basically, they are both icy moons. All three of them are icy moons of Jupiter that may have subsurface oceans, and they are also all three of them are among the 4 largest moons of Jupiter. The band positions on Europa, Ganymede, and Callisto are all shifted in the opposite direction from that expected for CO2 trapped in amorphous water ice, and do not match the shift expected for CO2 clathrate either. Clathrate, I have that defined. A clathrate is a compound in which molecules of one component are physically trapped within the crystal structure of another, although CO2 in clathrates has 2 discrete band minima. At the cryogenic temperatures and near vacuum pressures on the surfaces of these moons, CO2 adsorbed, not absorbed, adsorbed onto phyllosilicates produces V3, that's the band we're looking at, peaks that in some cases match those observed on Ganymede and Callisto. Although phyllosilicate minerals have not been identified on their surfaces, and we consider them implausible for Europa's salty resurfaced terrain. Again, I can't tell you what phyllosilicates are, but this paper is saying they're not here anyway. We have not identified any laboratory data that both match the wavelength of Europa's 4.25 micrometer CO2 peak and use a host material that we consider plausible on the basis of Europa's known surface composition. The substantial difference between the CO2 bands observed on Europa compared with those on Ganymede and Callisto indicates a different trapping mechanism, host material, or both. Okay, see what's being said here? There is CO2 trapped in material on Ganymede, Callisto, and Europa. However, the material that it's trapped in and or the mechanism that has caused it to be trapped in said material is different on Europa than it is on Ganymede and Callisto. This is consistent with the apparently different origins of the moon's CO2, which has been associated with older, darker terrain on Ganymede. That's a huge difference. The CO2 on Europa, as we've been saying throughout this paper, the most CO2 on Europa is found in some of the youngest parts of Europa's surface. And with craters and magnetospheric processes on Callisto, another big difference, we have already discerned that this CO2 is not related to impacts, craters, meteorites, etc. The V3 CO2 bands observed on several moons of Saturn are also shifted to higher frequencies, but vary in wavelength by up to 0.014 micrometers between the different bodies, with Dione and Hyperion providing the closest matches at 4.253 micrometers and 4.252 micrometers, respectively, to Europa's band position, although still not an exact match. The positions of these bands on Dione and Hyperion indicate trapped CO2 associated with other materials or ices, but the specific hosts are unknown. The CO2 peak at 4.27 micrometers observed on Europa is consistent with the position of 4.267 to 4.268 micrometers for pure CO2 ice, which is, as we've said, too volatile to be stable at Europa's surface conditions. Either there is another unknown trapping mechanism that produces a minimal band shift, or a single trapping mechanism that causes band splitting, perhaps due to distinct trapping sites within a single host material, as in CO2 clathrate, which has a double peak. Okay, so what this is saying Their explanation for why they have two CO2 peaks is that there could be a trapping mechanism for the CO2 in Europa's surface material that we are not aware of that produces minimal band shift, meaning that the 4.27 micrometer peak that they see just doesn't move very much to a different frequency. Recall that we kind of went over this earlier in the paper. The structure of your material can adjust where your spectral features show up by a little bit. And they're saying that that could be happening due to an unknown trapping mechanism, or it could be that both of their peaks, 4.25 and 4.27 micrometers, are due to a trapping mechanism that splits the band into two spectral features. The band depths of both the 4.25 micrometer and the 4.27 micrometer peaks are strongest in Tara Regio, but their ratio varies across the surface. As you see, within Tara Regio and across the equatorial latitudes, the 4.25 micrometer peak dominates, whereas the 4.27 micrometer peak is stronger across the northern latitudes, which are colder and more enriched in water ice. That is what you see in figure 1 here, and also in figure 2b, how the depths of these spectral features vary depending on where on Europa's surface the spectra was taken. Their explanation for that is, we suggest that low temperatures, ice abundance, or both could be related to the longer wavelength peak. Implications for Europa's atmosphere and ocean. We interpret the observed association of CO2 with large-scale chaos terrain as indicating emplacement of carbon from the interior. CO2 is on chaos terrain, therefore, it's from Europa's interior. The carbon is probably supplied as CO2, formerly dissolved in the subsurface ocean, but it could also be in the form of other carbon-bearing precursors. Emplacement could have occurred during the formation of such disrupted regions with potential mechanisms, including subsurface upwelling, melt-through, and ice collapse above shallow subsurface liquid. That's the upwelling of buoyant material. Melt-through is the one of the other possible mechanisms for chaos terrain formation. The words melt-through don't really sound to me like it's talking about the brine one, but I feel like that's the only one that it hasn't mentioned. And ice collapse above shallow subsurface liquid. That's the meltwater lens one. At the surface, the volatile CO2 must be trapped in one or more other materials, but we expect ongoing sputtering of Europa's surface to release some CO2 into Europa's tenuous atmosphere. Photoionization and interactions with Jupiter's magnetosphere would then remove CO2 from the system, as has been predicted for Callisto, where the expected timescale is about 4 years. Photoionization is when electromagnetic radiation causes an electron to escape an atom, leaving it ionized. CO2 that enters the atmosphere but is not immediately removed is unlikely to exit the atmosphere but could instead hop across Europa's surface, as has been simulated for Iapetus, was that it? Until it is either retrapped or lost. Therefore, a continual or recent supply of CO2 is required to explain the observed CO2 on Europa's surface, which is consistent with the maximum CO2 band strengths being associated with the youngest terrain. They are saying that there must be some sort of continuous or recent resupply of CO2 to Europa's subsurface ocean. Our interpretation implies that carbon, a biologically... we're on the last paragraph, okay? Listen up, this is important. Our interpretation implies that carbon, a biologically essential element, is present in Europa's subsurface ocean and has reached the surface ice on a geologically recent timescale. If this carbon was delivered as CO2, and if that CO2 is representative of the carbon redox state in the ocean, then a highly reduced ocean chemistry is unlikely. An oxidized ocean would instead be consistent with the proposed downward delivery through the ice crust of radiolytically produced surface oxidants, such as O2 and H2O2, on geologic timescales. An ocean rich in CO2 would also be consistent with slightly acidic conditions and a metamorphic origin of the ocean. That's it, that's the whole thing. But let's go over this last paragraph a little bit more. They're talking about what implications their results have on what we can say about Europa's subsurface ocean as a whole. Specifically, let's talk a little bit more about the carbon redox state that they mention. So I'm just going to read you my note verbatim. Reducing versus ionizing. There's a type of chemical reaction called an oxidation reduction, or redox reaction, where electrons move from one atom or molecule to another. These reactions are essential to life as we know it. One half of a redox reaction is the oxidant, which gains the electrons through reduction. The reductant loses electrons through oxidation. So this is discussing the ongoing efforts to determine if Europa's subsurface ocean is reduced, meaning it has gained electrons, or if it is oxidized, meaning it has lost electrons. Oh, and metamorphic means having undergone transformation by heat, pressure, or other natural forces. That's the whole thing. Oh my God, that was a lot. I'm exhausted.